Good evening. Quite a lot is going to happen in the sky, so let's begin with the eclipse of the moon due on May the 4th, when the moon passes into the shadow cast by the Earth. The moon rises partially eclipsed, and it will be total just before 9 o'clock. And here's a lovely picture of a past total eclipse taken by Ian Clark over Canterbury Cathedral. So let's hope for clear skies on May the 4th. I won't say an eclipse is important. It's not. It's lovely to watch. I've had many letters about the brilliance of the planet Venus, which really is now quite spectacular. Venus is really brilliant, and it can even cast shadows. That's not all. We have now a couple of comets, Chris.
We do. Comets Linear and Neat. Now, they're best placed for southern hemisphere observers, but even up here in the north, they might both reach naked eye visibility. They're certainly obvious in binoculars. Let's take Comet Neat first, which is the one we get the best view of. It's just moving past the sun now, and in the west, after dark, you'll see it moving through the stars of Gemini over the course of the next month. By the end of the month, it will be visible even after the sky is completely dark. But the comet should be more active now. It's already gone past the sun, so we need to trade those off. But it should be quite a nice comet, about the same brightness as Halley was back in 1986.
Because one never knows. Comets are like politicians, most unreliable.
That's right. And the other one, Linear, we'll see at the end of the month. We just get a glimpse of it from here in the north, down in the west, deep in the twilight. But you never know what it will be doing by then.
And of course, Saturn's in the news. The Cassini probe is on its way there now, and it's already sent back some amazing pictures of huge storms on Saturn.
That's right. This video which it sent back, it's 2 months away from going into orbit, but we're already getting beautiful pictures back. And this is an absolutely wonderful, detailed view of two storms colliding, coming together, and forming one single event. It's the first time we've seen it in this much detail.
Of course, Saturn is the windiest planet in the entire solar system.
That's right.
And we'll hear a great deal more when Cassini goes in. Of course, we'll cover it very carefully on the sky tonight.
Absolutely. It's going to be exciting.
It is indeed. And now, on to our main programme, Star Formation. And we're glad to welcome Dr Derek Ward-Thompson of Cardiff University. Derek, welcome to the sky tonight.
Good evening, Patrick. It's very nice to be here. Thank you.
First of all, exactly what is a star? Our sun is an ordinary star, and it's 93 million miles away, and that's known as the astronomical unit. And the sun is a huge globe of hot gas, very hot gas. Near the middle, the temperature must be something like 15 million degrees. But how is it shining? It's not burning. A sun made up of coal entirely, and burning as fiercely as the real sun does, would turn to ashes in a few million years. And we know our sun is very old. Our Earth is about 4.7 thousand million years old, and the sun's older than that, so it shines by an entirely different way.
What this animation shows us, we go down through the turbulent outer layers of the star. We get hotter and hotter until we reach the core, where the temperature, 10 million degrees or so, is high enough to allow nuclear fusion to take place. So protons, shown here in orange, collide, form first deuterium, then helium, and then finally stable helium with 2 neutrons and 2 protons in the nucleus. And that process loses mass. The sun loses 4 million tons of mass every second. And from Einstein's famous equation, E equals mc squared, mass corresponds to energy. So each time this process happens, each of these collisions, which incidentally gives off the light that we see from the sun as well, produces energy. And it's that energy that keeps the sun supported and radiates out into the rest of the solar system.
And at the moment, the sun is in a stable state, what we call the main sequence. It will stay there for a couple of thousand million years yet.
That's right, until all the hydrogen fuel is used up in the centre of the core.
Right then, going back to the beginning, just how is a star born?
Well, Patrick, when you look up on a dark night, you can see stars, and you tend to get the impression that the space between stars is completely empty. Of course, this isn't the case. If you look at long enough wavelengths, then you can see that there is a great deal of matter between the stars. This consists of gas and dust. The majority of it is hydrogen gas, which is the most abundant element in the universe.
It's very tenuous.
But it's extremely tenuous. If we had some of this in the lab, we'd call it a very good vacuum. However, of course, space is so large that there is sufficient mass here to form the next generation of stars. And this is where stars come from. we can see in this picture here a nice view of Orion, and we can see these, what we call clouds between the stars. We call them clouds because they look a little bit like clouds here on Earth, although of course they're not like that in the slightest. But these are the places where new stars form, and they're forming all the time. What we can see here is the famous Orion Nebula, and each of these bright regions is a region where an individual star or binary system is forming. The Orion Nebula isn't the only place in Orion where stars are forming. This region here is known as Orion B and is slightly above the belt of Orion. The bright regions that you can see here are the places where stars are about to form or are actually forming today.
But of course that's only part of a huge agglomeration of gas and dust which extends right over the whole constellation.
Let's go back to the very beginning. Just how does a star start to form?
Well, Patrick, you start with this gas and dust between the stars, and it's all stirred up by winds from the stars. We know the sun has a solar wind. All stars have a similar wind. This creates turbulence in this matter, and gradually within the turbulence, some regions will form which are more dense than other regions. Then the gravity from this denser part pulls together matter from the rest of the cloud, and gradually the material starts to collapse down onto the central seed, if you like, we call a protostar, the thing that's going to form a star. This is the constellation Ophiuchus. The bright band you can see across the bottom of the image is the plane of the Milky Way. But if we zoom into this region just above the plane in Ophiuchus, going to longer wavelengths, we can see regions where individual stars are forming. These are the brighter regions seen against the more wispy background. If we close in on this region, we can see the detailed structure of density and temperature. This false colour image shows you in red and in white where the most dense parts of the cloud actually are. And what we can also see from this image is that things aren't always simple and spherically symmetric.
And everything really depends upon how much mass there is, because stars are very different.
That's right. As everything falls down onto the central protostar, the very central core of that gets denser and denser, and therefore warmer and warmer. And eventually we cross the critical temperature and nuclear reactions can begin. And that's what powers the star. We say the star's switched on, and that's the birth of the star at that moment. As you say, how much matter ends up on the star can determine everything. Our sun is an ordinary dwarf-type star. It's not particularly large. Some stars, such as Deneb in the constellation of Cygnus, are much bigger and have much shorter lifetimes. Large stars live fast and die young compared to slow approaches like our sun.
After all, our sun is losing mass at the rate of 4 million tons every second.
Yes, there's plenty left, though.
Well, Deneb, far more luminous than our sun, is wasting away much more quickly than that.
That's true.
How long does it take a star to form?
Well, the sort of timescales we're talking about are typically measured in millions of years. And of course, it's very difficult for us to observe the whole process because we can't hang around that long and watch it, of course. But what we can do is we can look at places where we think stars are about to form and use that to give us an indication of what sort of stars might form.
I think people tend to forget that stars are very often binary pairs. I mean, our sun is a single star, but most stars are binaries, and that's very important information.
That's correct. Something like 2/3 of all stars live in binary systems. And until recently, we've had difficulty to explain that observation. And in actual fact, if you look at the younger stars, even more of them are seen to be in binaries or higher multiples. This is a computer simulation. The black dot that you can see in the centre is the first star that's formed from this cloud. And then we see, as the material falls in under gravity, a second star is actually formed, orbiting around the first star. This is a binary.
It seems common sense that stars form close together in the dense cores of these nebulae. Look at the Pleiades. That's a whole load of new stars that have formed out of a single nebula. But the question is exactly how close do they get, how many of them form binaries actually orbiting each other, and all of this we need to make sure our theory gets right.
We now believe that something like 2/3 of all stars live in binary systems or higher multiples, triples and quadruples and so on. And it's been a problem for star formation theory to actually explain this large number of binary stars. In this simulation, a star forms at the middle, and then in the turbulent structure around about, more stars form. You can see a binary star orbiting around the central star, and in fact another star is also formed which is finally ejected from the system. So we're left with what's known as a hierarchical triple system of a binary orbiting the single star. Until recently it's been very difficult to predict this because the level of turbulence that was needed in order to create multiple stars was much larger than we could see in the observations of these clouds. However, these latest simulations show that even if you start from relatively low levels of turbulence, such as we observe in space, then you can actually generate the correct number of binary stars.
There's another interesting effect as well. You're talking about what happens immediately after the star's switched on. Well, of course, you get light and radiation coming out into the dust that surrounds it. Now, that has a number of interesting effects. One thing is, we know we form planetary systems around these stars. I don't think we want to get into the details now, but the dust that's left over can go on, and we think that might go on and form planets. The other thing that happens is, in these, what we call hot cores around these newly formed stars, some quite complex chemistry can go on. We said at the beginning that most of the matter in the universe is hydrogen, and indeed most of the gas that collapses is hydrogen. But later on, we produce observable quantities of some quite complex molecules, alcohol, for example, ethanol we see, and even going up to some of the in some cases, we see the very simple amino acids, the building blocks of life. But you get this complex chemical sequences. And by modelling that in the computer as well, we get a whole wealth of other information about the star-forming regions. It's sensitive to the temperature and the density, so we can use chemistry as well as physics to try and probe these regions.
Because the stars have an immense range of both luminosity and in size. I mean, there are stars that are bigger than the Earth's orbit around the Sun, and stars that are millions of times brighter than our Sun. And of course, small ones that never really got going.
And that's one of the biggest problems, I think you'll agree, Derek, for modern star formation theories, is to try and predict simply how many large stars there are compared to how many small, what we call the mass function.
Do theory and observation agree there?
Well, this is an interesting one, Patrick. This has been known about now for 50 years. 50 years ago this year, a chap by the name of Edwin Salpeter published a paper in which he showed that the relative numbers of large stars compared to small stars obeys a fairly strict function. And what's been discovered since then is that more or less wherever you look in the universe, you see this exactly same function, this Salpeter shape of the relative numbers of large stars and small stars. And astronomers have puzzled over this one for decades, literally. And what we've seen recently is that if you look at the clouds where stars are forming, then they also show this same Salpeter function, which in itself is interesting because it says that the reason stars are the size they are is because the things they form from are the size they are.
But now, of course, now we need to explain why the cores that they form from have that particular range of masses.
That always seems to be the way in astronomy. You answer one question just to raise another one.
Well, of course, we do have what we call starburst galaxies.
That's right. These are galaxies which are undergoing huge amounts of star formation. And it seems possibly every large galaxy went through a starburst phase. And we can see the signature of star formation by looking at the right wavelengths, for looking for the dust and these bright young stars. We can see that from a great distance. Sometimes that's associated with active cores at the centre of the galaxies, sometimes to do with colliding galaxies. When two galaxies collide, obviously you get shock waves going through the dust, and as you said, that sort of thing, that turbulence triggers the star formation.
Well, eventually our galaxy is going to collide with the Andromeda galaxy, which is now well over 1 million light years away.
That's right, and that will produce a huge burst of star formation. At the minute in our galaxy, star formation seems to be happening along the spiral arms because they're shock waves that move round the galaxy, and so they bring with them star formation as they rotate around the galaxy.
Well, our galaxy contains something like 100,000 million stars, but what is the rate of star formation?
Well, that's an interesting question, Patrick, because if we actually sum over the whole of our galaxy, we see that the rate of new stars being born is the equivalent to one new star the size of our sun every year. And this may seem like a lot. However, when we look at the clouds from which they're forming, the problem that we have is that in fact they should be forming far more stars than we're seeing. So clearly something is preventing them just from simply collapsing under gravity, and there must be some additional process taking place here that's actually slowing down this collapse.
Have you any idea what it is?
Well, we believe that it may be turbulence. While on the one hand turbulence may well trigger some star formation, on the other hand it may actually cause the formation rate to be lower in other places simply by hindering the gravitational collapse.
We are, of course, getting these magnificent pictures of star-forming regions, mainly from the Hubble telescope.
And from the Spitzer Space Telescope, which is NASA's new observatory, which looks in the infrared region of the spectrum. And for example, take this image of M81. So the first image you can see is the visible light, it's a Hubble image, and then we can zoom in and we can look at what the difference is in infrared light. And what it does is it picks out the dust and it picks out the star formation. We really need to look in infrared. So we're getting some amazing images back from Spitzer. And that's operating for at least the next, is it 2 years, I think?
That's right, and the infrared is very important because, as we said earlier, the dust in these star-forming regions only accounts for about 1% of the mass, but it actually effectively obliterates the optical light coming from these regions, and so that's why we have to go to the infrared and fly these infrared satellites. And what's remarkable is just by going to longer wavelengths, suddenly you can see right into the middle of these regions and see where all the action's happening now.
What exactly is this dust?
Well, yes, we know there's quite a lot of dust there. What we actually mean, what it is it's rather like, it's made of the same material as the sand on the beach. However, it's not as large, the particles are not as large as sand grains on the beach. They're more like the typical size of smoke particles, for example. And like smoke particles, they're very good at blocking out light.
So my memory goes back to the time when we didn't even know why the stars shone or how they formed. But is it fair to say now that you really have a pretty good idea of star birth?
I suspect that we understand the broad brush picture, and we're certainly making progress on that. The binary fraction, the relative numbers of larger stars and smaller stars, but there are still a great deal of unanswered questions. And in the future we have there are plans for new telescopes, new satellites. The Herschel satellite is a European Space Agency satellite due to be flown in the next few years, which in itself will also answer some more of these remaining questions.
Well, certainly we've come a long way, and we'll go further still. And looking now up at the stars, they're all suns, and the fact that our own sun was born in this way something like 5,000 million years ago. We've got a long way to go yet. Chris, Derek, thank you very much.
Thank you, Patrick.
It's newsletter time. If you want your newsletter, then send your stamped addressed envelope to The Sky at Night, newsletter number 93, room G06, BBC Birmingham, B57QQ, and we'll send you your newsletter. Now, something very exciting is coming up. On June the 8th, there's going to be a transit of Venus. The planet Venus will pass in front of the Sun for the first time since 1882, so no one now living can ever have seen one. And, of course, we'll be covering that in a programme, and we hope showing you the transit direct. So until then...